morning, students. So in this session, let us look at half-wave rectifier. Okay, so we have already discussed this half-wave rectifier in during the clipper session, right? So a half-wave rectifier is nothing but a diode that is in series with a resistor, and you take the output across this resistor. Okay, so here the input is of course sinusoidal in nature. Okay, so the input expression of the sinusoid is given by Vi is equal to Vm sine omega t, where Vm happens to be the peak value, okay, and minus Vm is the negative peak. Okay, so this much we have seen in the previous lecture as well. So what happens in the positive half cycle is this diode is forward biased, and when this diode is forward biased we replace it with a short circuit. So the equivalent circuit looks something like this. Okay, so this diode is replaced by a short circuit over here. What happens is V0 is directly equal to Vi. So from 0 to T by 2, okay, when Vi is greater than 0, the diode is forward biased and V0 is equal to Vi. Okay, what happens when the sinusoid goes into the negative half cycle? Okay, when it goes into the negative half cycle, the diode is reverse biased. Okay, when the diode is reverse biased, that is reverse biased when the P side is at a negative voltage or at a lower voltage compared to the N side. Okay, so when it is reverse biased we replace it with an open circuit, because we are taking the voltage drop across this resistor and there is no current through this resistor. So V is equal to IR. So because I is equal to 0, so voltage across this is also equal to 0. So between time t by 2 to t, the voltage is equal to 0, and between 0 to t by 2, okay, we know that V0 is equal to Vi. So this is called half wave rectification, and we have already discussed this in the clippers. Okay, but in this session we'll be discussing more about this particular wave. Okay, so this is the half wave rectified wave, and we shall try and understand its properties. And there are three very important properties. Okay, so there are three very important properties of any rectified wave. Okay, so those three important properties are: the first one is the average value or the DC value. So average value or the DC value of the rectified output. Okay, so the second one is the RMS value. So second one is the RMS value. So RMS stands for root mean square. Okay, so the RMS value of the rectified output. And the third one is the ripple factor. So here while discussing the ripple factor, I'll give its definition and what it signifies. Okay, so first let us discuss the average value of the rectified output. Okay, so for a half wave rectifier, this is the input output waveform, isn't it? If the input waveform is a complete sinusoid, the rectified output has only positive half cycles, but it has no negative half cycles, and the negative during the negative half cycle the output is completely zero. Okay, so here the DC value is 0, isn't it? Why? Because here the positive area and the negative area, they cancel out each other, and the VDC of the input signal is equal to 0. But that is not the case with our rectified output. Okay, uh, according to the definition, the average value or DC value, the definition stands as like this: 1 by t integral 0 to t v of t dt, where here v of t is my rectified output. Okay, now let us try and find the VDC value. Okay, so here let me change the base. Let me take the time period t to be 2 pi. Okay, so that means the input waveform V in becomes V in is equal to Vm 2 pi by t, and t is taken as 2 pi, omega becomes 1. So this is v in becomes something like this. V in is Vm sin t. Okay, right. Now let us derive the VDC value of the rectified waveform. Okay, from the definition, it is nothing but VDC is 1 by t. It is 1 by 2 pi, because t is equal to 2 pi. We have taken the base as t is equal to 2 pi. So this is 0 to 2 pi. Okay, the rectified output. Okay, the rectified V naught of t dt. But we know that V naught of t is equal to Vi of t from 0 to pi, and V naught of t is equal to 0 from pi to 2 pi. So plugging these conditions, what do we have is, we have something like this: 1 by 2 pi integral 0 to pi. Vi is nothing but Vm sin t e dt plus integral pi to 2 pi 0 dt. So that would give me 1 by 2 pi integral 0 to pi Vm sin omega t. Okay, so that would in fact result in something like this. So integral sin omega t is sin this omega is equal to 1, because our base is chosen as 2 pi. Okay, so this can be written as Vm by 2 pi integral 0 to pi sin t into dt. Okay, so that is nothing but minus Vm by 2 pi into cos t, and the limits go from 0 to pi. So that is nothing but minus Vm by 2 pi into cos pi minus cos 0. Okay, so we know that this is nothing but minus Vm by 2 pi. Cos pi is minus 1 if I am not wrong, minus cos 0 is 1. So this is nothing but 2 Vm by 2 pi, that is nothing but equal to Vm by pi. Okay, so the average value of the half wave rectified output is nothing but Vm by pi, that is nothing but 0.318 Vm. So 0.318, this is nothing but 1 by pi. Okay, right. So that derives the average value of the rectified output. The second important property is the RMS value. Okay, so RMS value again has its definition. Okay, the definition of RMS value. So VRMS is nothing but under root 1 by t integral 0 to t. This is V square of t dt. Okay, again we are trying to find out the RMS value of the output waveform. So again, like discussed earlier, our base t is equal to 2 pi, that would result in omega is equal to 1. So if I plug in terms here, I'll get VRMS square, and I'll square on the both sides. I get something like this: 1 by 2 pi there is nothing but 1 by 2 pi integral 0 to pi. Remember, from the output is present only from 0 to pi. From pi to 2 pi it is 0. So, and from 0 to pi it is nothing but input. So input is nothing but sine square t dt. Okay, again if you go to your +2 trigonometry basics, it is known that sine square t is nothing but 1 minus cos 2t by t. This has Vm. This has Vm over here. So this has Vm square over here. Sorry for that. Okay. So now let us go ahead. Okay. So I can write this as 1 by 2 pi into 2, the numerator can be Vm square integral 0 to pi 1 minus cos 2t dt. Okay, the one. So this can be, I am just plugged in this into this, so the denominator is 2, it got multiplied by 2 pi here. Okay, so this is nothing but Vm square by 4 pi into, if I do the integration, 1 dt is t minus integral cos 2, sorry, integral sin 2t cos 2t is nothing but sin 2t by 2, and the limits are from 0 to pi. Okay, right, now if I substitute the limits, what do I get? Vm square divided by 4 pi into, so t is upper limit pi minus, what is sin pi? Sin pi is 0 minus of, okay, lower limit t is 0, so this is 0 minus, what is sin 0? Sin 0 is also 0. So what are we left with? That implies Vrms square is nothing but Vm square by 4, that is nothing but Vrms is equal to Vm by 2. So for a half wave rectifier output, the RMS value Vrms is equal to Vm by 2, and the DC value, like we have discussed earlier, is equal to Vm by pi. Okay, now let us derive the third important parameter. So this has been derived. Now let us try and derive the ripple factor. Okay, now let us try to understand ripple factor first. The third thing is the ripple factor. So what is ripple factor? So ripple factor R is nothing but ratio of RMS value of AC component of the signal. Okay, it is the ratio of RMS value of AC component of the signal to the average value. Okay, so average value is nothing but it is also called as DC value. So this is the definition of ripple factor. Remember, the numerator here is RMS value of AC component of the signal. It is not Vrms. What is this not equal to? Is this is not equal to Vrms. Okay, so let us now try to understand what is the RMS value of this AC component. So let us try to understand this. Okay, right, so we'll have a look at the half wave rectified output. Okay, so it has both the components. It has an AC component in the first half cycle, and it has a 0 DC component in the second half cycle. If you remember the output of the half wave rectifier, from 0 to t by 2 it has an AC component, from t by 2 to t it has a DC value. Okay, or of course the DC value happens to be 0. Okay, now let us try to, so any given voltage V has both components AC and DC. Okay, so from this it can be written as AC component of the signal is nothing but the entire signal minus the DC component. Okay, now what are we supposed to find out in order to find the ripple factor? We are supposed to find out the RMS value of AC component. So from definition of RMS value of AC component, this is nothing but square root of 1 by t integral 0 to t VAC square dt. So extending it on to the right hand side and substituting t is equal to 2 pi, so that would result in something like this. Okay, so on the right hand side, that is nothing but 1 by 2 pi integral 0 to 2 pi. So right hand side is nothing but v minus vdc the whole square dt, and this entire thing is under root. Remember, this is root mean square value, so this entire thing is under root. Now what I'll do is I'll expand this. So this is nothing but 1 by 2 pi, okay, integral 0 to 2 pi. What is a minus b whole square? A square minus 2ab plus b square. This is nothing but v square minus 2v into vdc, okay, plus VDC square, okay, this entire thing into dt, and the whole thing is under a square root. Okay, now what I'll do is I'll split the integrals now. So if I split the integral, what do I have? I have 1 by 2 pi integral 0 to 2 pi v square, okay, uh, dt minus 1 by 2 pi integral 0 to 2 pi, okay, 2v vdc dt, okay, plus 1 by 2 pi integral 0 to 2 pi, okay, vdc square dt, and this entire thing is under the root. Okay, so this is nothing but from the definition, this is nothing but okay, RMS square, isn't it? So this is nothing but VRMS square. So we have seen earlier that what is VRMS square? So VRMS square is nothing but 1 by 2 pi integral 0 to t. If we square on this both sides, we get VRMS square is 1 by t integral 0 to v square dt. Okay, so this is of the same form, isn't it? So that is why it is VRMS square. And if we observe carefully, okay, so this is nothing but 2 2 into 1 by 2 pi integral 0 to 2 pi v dt into vdc, okay, plus 1 by 2 pi, okay, if I do the integration, this is vdc square, 1 dt is nothing but t, and if I substitute the limits, this is 2 pi minus 0, and this entire thing is under a square root. Okay, so what am I left with here? So this is nothing but VRMS square minus 2 into, this is nothing but the expression for VDC, isn't it? What is VDC? VDC is nothing but 1 by 2 pi integral 0 to 2 pi VDT. So the same thing is happening here. So this is nothing but VDC and into this VDC, okay, plus this 2 pi and 2 pi get cancelled out. What we are left with is again one more VDC square, okay, and this entire thing under root. So what we are left with in effect is VRMS square minus VDC square, entire thing under root. So what is the expression for the RMS value of AC component? VAC is nothing but, we computed it as, what is VAC? VAC is nothing but square root of VRMS square minus VDC square. So this VAC is usually referred to as VRRMS. Okay, right. Now let us try to find the VRRMS. Okay, so what is VRRMS? VRRMS is, what is VRMS of half wave rectifier? That is nothing but Vm by 2, so that is nothing but Vm square by 4. What is VDC? VDC we computed it to be Vm by pi, so this is nothing but Vm square by pi square. So if we compute this, this will turn out to be 0.385 Vm. So this is approximately VRRMS is equal to 0.385 Vm. Now we are trying to find out the ripple factor R. So the ripple factor R is nothing but VRRMS, that is nothing but the RMS value of the AC component of the signal divided by VDC. So that is nothing but 0.385 Vm divided by Vm by pi. Okay, so this gives us around 1.21. So what is the ripple factor of a half wave rectifier? So the ripple factor of a half wave rectifier is 1.21. Okay, and if you are trying to make a circuit, remember half wave rectifier is used in order to convert AC to DC, isn't it? Okay, so here the ripple factor is more than one, indicating that the half wave rectifier output is more of an AC signal and less of a DC signal. So there is a long way to go before we get the AC signal. Okay, so these are the three important parameters. Okay, so we have derived all the three properties. Okay, one is the average value, the other is the RMS value, and the other is the ripple factor. So we have derived all these three. Okay, now let us try to improve the output of this half wave rectifier. Okay, by introducing a capacitor filter. Okay, so the next topic is introducing a capacitor filter in half wave rectifier. Introducing a capacitor filter. So let us see how that circuits looks like. Okay, so this is the circuit. This is nothing but if you don't have the capacitor, that is nothing but the half wave rectifier, isn't it? Okay, now with the capacitor, how does this circuit behave? So let us try and quickly analyze. This is very easy. Okay, so without the capacitor, we know that it is halfway rectified output. It goes on something like this. But what happens with the capacitor is, okay, so once the input waveform is gone till the peak value, that is when the diode is forward biased. Okay, so the capacitor is also charged to the peak value. So if the peak value of the input is Vm, okay, so the capacitor is also charged to the peak value. Okay, now once the input signal is going from T by 2 to T, that is the negative half cycle, once the input signal, or rather in this case, once this input signal is going down from the peak value, okay, so what happens here? Here the capacitor is already charged to Vm. Now because the input waveform is going below Vm, so what is the situation here? The P type, here the P side has a lesser voltage when compared to the N side. So what happens immediately is nothing but this capacitor, sorry, this diode gets open circuited. So there is open circuit. What happens is, since the diode is now charged to Vm, okay, now this this capacitor is charged to the value Vm. Now this capacitor starts discharging through the resistor. So what happens is, this capacitor starts discharging, okay, and until the Vm until the next until it catches or until the diode becomes forward biased again. Once the diode becomes forward biased again, it becomes charged till Vm, okay, the peak value again. Once the input is going below Vm, okay, the capacitor discharges. Okay, so this goes on. Okay, so if you consider the two outputs, if you consider half wave rectifier without the capacitor, it is something like this. Okay, and if you consider half wave rectifier with the capacitor, what is it doing? It is doing something like this. Okay, so if you compare these two, our main objective is to go from AC signal to a DC signal. If you see this signal with the capacitor, it is more close to the DC signal, isn't it? It is of course not pure DC, but we things seem to be getting, we are getting near to DC, isn't it? So this is how the half wave rectifier with a capacitor filter behaves. Okay, so you will get a not a pure DC, but this is called a, so usually this is called pulsating DC. Okay, this is called pulsating DC, and half wave rectifier with capacitor filter is called is usually called as rippled AC. Okay, so that is how half wave rectifier with a capacitor gives us a near DC signal. Okay, so this is nearly DC, but not exactly. This is almost near to this, but it still has some ripples. Okay, so that is how our half-wave rectifier tries to convert an AC signal to a DC signal. Okay, so if you have any doubts, please do message me or mail me or ask me over phone. Thank you.